Swayam Prabha. Digital India. Educated India.
In this lecture, we will discuss about airfoil geometry and we will revisit the forces and moments acting on an airfoil, which we had discussed earlier also. Let us make a small sketch which will be useful for us to discuss about the airfoil geometry. There are two very important points on the airfoil. One is the leading edge and the other is the trailing edge. Leading edge is the most upstream point on the airfoil surface and the trailing edge is the most downstream point on the airfoil surface. The flow may be approaching from the left to the right. Now, if we connect the leading edge to the trailing edge using a straight line, then that forms the chord line. This is a straight line which connects leading edge with trailing edge. You can abbreviate this as LE, this as TE. Now, there is another very important curve. Let us mark it with some other color. And this curve is called as the camber line. You can see that it is offset from the chord line. Moreover, it is a curve, it is not a straight line. Now, the idea is that about this camber line, we apply some thickness to develop the airfoil geometry, and that thickness is equally distributed above and below the camber line. So, if I say that at a particular location of the chord line, which we can denote by the x coordinate of a particular point, say this is the point you choose on the chord line. So, it has a particular x coordinate. So, along that x coordinate, if you rise and you meet the camber line, then this is the intersection point of the camber line. Now, at that location, if the total thickness is T suffix p, because the point that we have chosen on the chord is p, and correspondingly the thickness that we are defining at that location is T p, then half of Tp would be above the camber line and half of it will be below the camber line in order to define these points which lie on the surface of the airfoil. That is the concept of equally distributing the thickness above and below the camber line. Now, this principle is followed at all points along the camber line in order to give rise to this airfoil shape. That means, we begin from the equation of the camber line. So, if we have the equation of the camber line available, to that equation we have to just add Tp by 2 and subtract Tp by 2 as a function of x. Most often, instead of using dimensional coordinates, we would like to use non-dimensional coordinates in the form of x by c as we move along the chord. So, the x by c corresponding to leading edge would be 0 and that at the trailing edge would be 1. That means, x by c can vary from 0 to 1. You would have a decimal value of any point lying between leading edge and trailing edge accordingly. This camber line is often called as the mean camber line, and greater the camber of the airfoil, the greater is the curved nature of the airfoil. What happens if the camber of the airfoil vanishes? You can imagine that the camber line will come and merge with the chord line, and then you will have an airfoil which does not have the curvature in the sense of the camber line. Now, airfoils which have a certain amount of camber are called as cambered airfoil. At any x by c location, the camber is defined by the difference in the y coordinates between the camber line and the chord line. So, at this particular location, if you define a point q on the chord line, then this is the camber corresponding to the point q, which has a x by c q. If you look closely at the leading edge of the airfoil, right at the leading edge, you can imagine a circle with a radius approximately of the order of 2% of the chord. That means, this is the leading edge radius. We would call it as the leading edge radius. It is circular in shape. So, this is as far as basics of airfoil geometry is concerned. Now, recalling about the forces and moment acting on an airfoil. From our earlier lectures, we know that two types of forces basically act on the airfoil in the form of stresses. One is pressure, the other is shear stress or skin friction. And as a consequence, because of the distribution of pressure and tau on the airfoil, what happens finally is a resultant force is produced and a resultant moment is produced. By convention, we take the moment to be positive if it is going to pitch up the nose of the airfoil. That means, it has a tendency of increasing the angle of attack of the airfoil. So, let us say if the flow is approaching the airfoil at an angle, the angle is between the chord line and the velocity vector, then that is the angle of attack. We are recalling some of the things we have already learned, that if you resolve this force R into two components which are along the chord line and normal to the chord line, that is one way of resolving this force. Then what we get is the axial and the normal forces. So, this is one way of resolving the forces. Another way of resolving forces is to consider the flow direction and imagine that the flow vector direction is parallel to this. You try to resolve the force R into two components. So, this time it is parallel and normal to the velocity vector. So, this is how you can resolve the same force R into two sets of components. We have discussed this earlier. So, N is perpendicular to chord line, A is along the chord line, L is perpendicular to u infinity and D is along u infinity. Again, here we are considering that these forces are per unit span, in the sense that this airfoil section has a unit depth, and accordingly the force which would act on the airfoil section having that unit depth is what is considered over here. Now, the issue is that the overall distribution of pressure and shear stress, they are giving rise to the force and the moment that we are talking about. However, it is very important to understand that this resultant force R would act through which point. Can we keep this point, the location of this point, arbitrary? That is not possible. So, we have to look deeper into this issue and try to understand this issue. So, the answer to this question is that the resultant force R has to be located such that it produces the same effect as the distributed pressure and shear stress. So, we will try to do a little more calculation, a little more discussion on this to understand this issue. Now, we have already talked about the fact that there is a moment acting on the airfoil as well. So, if you look at the idea that can I have this force R located at a particular point, so that it gives me the moment about the leading edge point appropriately. For that, we will define a very important point which is called as the center of pressure. So, we are locating that force R at a point which is at a distance of x c p from the leading edge and marking the moment at the leading edge as m l e. This is the appropriate location which generates the exact moment about the leading edge m l e. So, if we look at the balance, how we would appropriately represent it? Leading edge moment is positive, by convention it is clockwise, and that is exactly represented by the moment created by this force N, which is acting at a distance of x c p from the leading edge, but in the counterclockwise sense. Obviously, the force A will not produce any moment about the leading edge, because it is lying on the chord and leading edge is a part of the chord itself. Therefore, it is only the normal force which will create it, and it exactly creates that much moment as the leading edge moment. So, if that is the case, then we get the coordinate of this point which we call as the center of pressure. So, let us try to re-emphasize the significance of the center of pressure once again by defining it. So, it is the location where the resultant of a distributed load which is created both by pressure and shear stress effectively acts on the airfoil. If moments of forces are taken about the center of pressure, the integrated effect of the distributed loads would be 0. Therefore, it is a point on the airfoil about which the aerodynamic moment which of course is pitching moment, is 0. Now, we may recall that the pitching moment equation, if we were to write down the pitching moment equation, that will show precisely how pressure and shear stress was integrated over the surface. So, we are recalling this equation where upper and lower surface pressure as well as shear stress participated in creating the moment about the leading edge. So, this is for the upper surface, and we similarly write it for the lower surface, and remember that the theta from point to point would depend on the surface geometry. So, we were just talking about the airfoil geometry few minutes back. Once you define the geometry, as you move from one point to the other on the surface of the airfoil, you get the x and y coordinates of those points, plus you get the slope of the surface, and accordingly the theta gets defined. So, that way based on a particular airfoil shape and a particular pressure and shear stress distribution, you would be able to integrate this. You can of course integrate it even in non-dimensional sense, in the sense of the coefficients, and then you would end up getting Cm, the pitching moment coefficient about leading edge. So, whether dimensional or non-dimensional, this is how you would go about calculating the pitching moment. And here in the context of center of pressure, we found that it is a point on the airfoil about which the aerodynamic moment, net moment will turn out to be 0. Now, we recall these equations that from the normal and axial forces, you could also work out the lift and drag acting on the airfoil section by resolving them appropriately by using the angle of attack. And for small value of alpha, cos alpha would be approximately 1 and sin alpha will be approximately 0. And therefore, there is a significant simplification, that lift will be approximately equal to the normal force, drag will be approximately equal to the axial force. Hence, the position of the center of pressure can be expressed approximately as negative of the pitching moment about the leading edge by the lift acting on the airfoil. So, we recall that we appropriately located the resultant force location such that the normal force placed at that location would create the exact moment about the leading edge. That was the whole concept. So, we would look at different equivalent ways of locating these forces, so that we can create appropriate moments acting on the airfoil irrespective of where we consider these forces. As such, the magnitude of the force remains identical, but where it is being applied on the airfoil will accordingly define the corresponding moment that will act on the airfoil. That is the idea. Now, one thing we can realize is that as the normal force or the lift decreases on the airfoil, that means the denominator here decreases, the center of pressure will increase, and when the force becomes really close to 0 or exactly 0, then the center of pressure will move to infinity. So, center of pressure is certainly dependent on the normal force or lift forces, and it is evident that that will happen with different angles of attack. We will see later that these forces are dependent on angle of attack. In an earlier lecture also we saw the lift curve, that means CL versus alpha curve, where you might recall that it looked somewhat like this. So, likewise normal force also is going to vary in a similar manner. So, they are strongly related, correlated with alpha, and therefore, as alpha changes their value change, and as you get closer to smaller values of n or L, then x Cp becomes exceedingly large, and in the limit it goes to infinity. Therefore, it is not a fixed point, it is not a fixed point on the airfoil, it moves around as a function of angle of attack. Now, we were talking about equivalent ways of calculating the moment that is acting on the airfoil along with the location of this force, the resultant force. So, let us try to draw a few cases which are equivalent to each other. It is the same airfoil at the same angle of attack, the same free stream velocity, therefore, the same pressure and shear stress distribution. So, all the three cases are identical, only difference is how we look at the location of the forces that are produced. So, in one case we are considering that the forces are acting at the leading edge, and correspondingly there is a moment about the leading edge. In the second case, we are talking about locating the forces at quarter chord. That means, this is the total chord length and this is approximately halfway. So, this is quarter chord. The same force and now, since they are acting at C by 4, which is the quarter chord, we will mark the moment as moment corresponding to the quarter chord location. And then finally, we will consider a case where the forces are at x Cp. So, corresponding to the angle of attack, whatever be the value of lift, accordingly the angle of attack gets accordingly the x Cp gets defined, like we saw in the earlier slide. So, these three cases can be represented through an equation like this. So, in the first case we have a moment about the leading edge and there is no moment due to the lift force, because it is acting exactly through the leading edge. So, moment at the leading edge can now be written as moment at the quarter chord minus L into C by 4, because moment at the quarter chord is again positive clockwise and then this is counterclockwise. So, it negates, and finally, this should be equal to minus x Cp into L, because now you have the moment corresponding to the force acting through xCp is equal to 0. So, what do you have? You have the m leading edge, for example, expressed as minus xCp into L, all right, because you have a 0 here, basically a 0 coming from m xCp. So, these actually connect between the three cases where we have different equivalent ways of specifying the force and moment system on an airfoil. The resultant force can be placed at any point on the airfoil as long as the value of the pitching moment about that point is also provided. And the beauty of the center of pressure is that you do not need to provide that pitching moment, because that by definition is equal to 0. So, in this lecture we discussed about airfoil geometry and we recapitulated about aerodynamic force and pitching moment on an airfoil. We discussed about the concept of center of pressure, and we would discuss about pressure distribution on an airfoil further in the upcoming lecture. Thank you.